Good day, everybody. My name is Muhendra. Today, I'll be presenting about my assignment regarding the production of methanol with integrated production of hydrogen. So, without any ado, let's first go into our presentation. Just a minute. All right. Sorry for the delay. So, with today's topic, which is the integrated reactor and suppressor system for methanol production, which also enhance hydrogen production. So my name is Muhendra. My metric number is 2500293 4, and this is an assignment under the subject of OBUI 5153. Okay, first of all, let's just go through a short summary. Why methanol? Methanol is a very comprehensive chemical that has been used and utilized in many productions. And of course, methanol is also key for many other derivatives, for example, formaldehyde, acetic acid, and also in recent study been used for in marine or aviation fuel blending. And of course, if we see at the production capacity and demand, it's been increasing time to time. So it shows us the needs for us to produce methanol in a much more sustainable way and also cost effective. Okay, in this case study of this production, I have chosen to produce my methanol via conventional syngas. The reasons why is because, first of all, is the technology maturity. Via syngas, it's been there for decades compared to other new methods of productions, which also makes it easier to be commercialized. And in case if there's a problem, and we is also proven method. It's much more a proven method. So that's one of the reasons. Second, Malaysian, we have abundance of natural gas availability, and we can use and utilize it to produce derivatives from natural gas into methanol and so on. And even from production cost wise, is much more cheaper and more reliable. So that's the reason why I chosen to do. Is I have chosen to produce methanol via syngas route. My project objectives is very clear. It's 5 steps. Define the route and justification as I did before, and evaluate 3 reactor systems and configurations. Select operation conditions and kinetics, and model it based on that. We will model it in our S1 HYSYS and evaluate in the economic and performance wise. So the design basis is based. We're going to produce 2,000 kgs of 2,000 kg per hour of pure methanol, which can be translated to 70,522 tons per year. So of course, in every production of methanol, we have to focus. There will be a key focus on what kind of key reaction that will take place. So it's a typical key reaction that usually take place where the reactants are C and CO2, CO and CO2, which is usually CO is much more preferred in the selectivity of residual methanol. And of course, this is also the catalyst you're going to be used based on industrial standard is either copper, zinc oxide, and aluminum trioxide. So in reactor selection and separator selection, I have decided to simplify it into 3, which first initially is a fixed bed tubular slurry bubble column and fluidized spray. However, because due to the commercially available in market and also other productions around the world, I have selected multi-tubular fixed bed with a boiling water cooling system. Separation system is via a flash separator and also distillation column. So moving on, the operating condition and also the reaction kinetics. The operating conditions are as stated below, as stated over here in the slide. where the temperature is between 220 and 400 Celsius within two reactors, and also pressure swing between 50 to 100 bar, where within the average of 80 bar. And the most importantly, we have able to have to maintain the hydrogen and CO2 ratio based to 2 to 1. And here, let's go to the heart of the presentation today, which is about regarding the process simulation. Okay, first of all, in our present in our in our particular process simulation is break into three parts of processes. First is the propane refrigeration loop, and it's followed by a natural gas, a gas plant synthesis, then syngas, then methanol. So to cut short, the propane refrigeration loop is created in order for us to make the natural gas, which is in the gaseous form, into a liquid form, in order for us to transport it easier and also to occupy a lesser space. So in every refrigeration loop, there will be four units, definitely: a chiller, a condenser, an expansion valve, and also a compressor. Where the targeted value for us in this particular refrigeration loop is negative 20 Celsius. Then we followed by our gas processing unit. So our gas processing unit starts with, let me minimize, okay. Our gas processing unit starts with a three-phase separator, because whenever we want to feed our any kind of feed into our demethanizer or deethanizer, we need to remove as much of water as possible. So we use a knockout drum, also a three-phase separator, to remove any kind of water or liquid condensate as much as possible. So by creating this unit operation, we are able to remove more water. Second, based on this three-phase separator, you can see there's one vapor line and one liquid line. So one vapor line will be going to a multi-plus heat exchanger, which is also known in the HYSYS as LNG exchanger. So what is so beautified about this LNG exchanger is that this LNG exchanger allows multi hot and cold streams, while the heat exchanger model only one side on the hot stream and also one side in the cold stream. So that's the reason why. But for us to able to get the design, it requires inlet and outer stream and pressure drop for each stream, and the hot and cold side designation. This will be estimated for calculation. So this will be calculated based on the processes that been feeding to be, which need to be cooled off, which need to be cold or hot to make it heat it up. Okay, so based on that, we were followed by the two distillation unit, which is in series form, which is the demethanizer and also the deethanizer. So the vapor phase of the hydrocarbon that are being processed in the turbo expander model has now isolated. Now we can turn back this into focusing in further separating the methanizer rich stream and also deethanizer mission, which is this can be further sell as our as a product as well. Okay, so before we are feeding into the demethanizer, there's also a cooler. So this cooler is helping us to gain a temperature almost negative 8.7. So it enables us to make the separation much more better in the demethanizer. So next from the demethanizer, we're going to eat into the multi heat exchanger, where to liquidify it, and also there's a certain traces of methane that been vaporized from the three-phase separator, is then go to the expander, then it's been further expand, which is then used as our feed flow to our syngas plant, where certain amount also of the gas can be exported as an LNG. Now, we are going to focus in our the most main part of the plant, which is our syngas plant and also a methanol plant, uh, which is already integrated as one unit. So the syngas plant from the syngas unit, which we produce much more richer methane composition. For example, as you see, the methane composition almost 0.92, which is much more feasible feedstock for us to produce syngas. So it goes to a natural gas compressor to compress the syngas, so that makes more easier for us to have a contact in our subsequent reformer and combustor in the process. So then it goes to a natural gas heater, where it enables us to heat for us to a temperature up to 370 Celsius, from 33 Celsius to 370 Celsius. Then any hydrocarbons heavier than methane is also removed in the splitter, which is where you can see the heaviest like isobutane, N-butane, and N-pentane, and also like and certain amount of water, and also a very less amount of octane, in order for us to make it much more richer feed into our reformer. So in our reformer, it's always we're going to see the sets of reaction where methane is going to be produced. Methane is going to be the feedstock, and where and water is also used. Where in this reformer, we will use steam SMR, steam methane reforming system, where methane and water are going to use as a feedstock to produce CO and hydrogen. So from the reformer, it goes to a combustor, where this combustor acts to react to further any methane that not been reacted into CO and hydrogen as well. But in the same time, there are other kind of reactions as well. If you see, methane, water will produce CO2 and hydrogen. Same goes here. That and any other hydrocarbons like ethane, which reacts to produce CO2 and water, and also methane fully oxidized into CO2 and water, and also the final reaction, which is propane, which is also the full propane and ethane that may be passed through from the splitter itself. So in here, we use an reformer steam, as this is a SMR, and combustor just purely an air. Okay, then once it pass through the SMR and combustor, we need to further cool down this gas, which is, I can say this is a quenching system, where from 790 Celsius to up to 35 Celsius, which is, so of course, in today's plant will be much more series of heat exchanger or train of heat exchanger. But for the sake of simulation, I've created only one heat exchanger that we are able to reduce the temperature up to 35. Then there's a water separator system to knock any water content in the system. And here we have a drama, which I can say this is a much more drier syngas, which already composed of CO, CO2, hydrogen, and also maybe unreacted methane. Then it's further compressed. Then it goes to our first reactor. Our first reactor is by design, there will be a methanol vapor and also unreacted, maybe methanol residues. So in this case, you can see in the first reaction, where CO2 hydrogen produce methanol, and the second is CO2 methanol produces methanol and hydrogen. Sorry. Okay, you can see methanol reacts with water to produce hydrogen and also CO2. Then followed by another reactor going through the same. So in the sense, it's a series reactor, the same process that goes on, where it's also the same kind of reaction, methanol to produce CO and reacts with hydrogen to produce methanol, and also CO2 to produce methanol. CO2 is which is our feedstock to produce methanol as well. Both are the configuration of the first reactor and second reactor is the same, where the temperature, as I say, will be 220 to 300 Celsius. So the temperature of the first reactor is at 250 and elevated in second reactor to 300. So it is like to say, this is to control the cooling of the both reactors instead of just having only one reactor. When we have two series reactors, easier for us to control the temperature as well. So then the methanol vapor then is being cooled down, go to a flash drum, where the unreacted vapors, which is more, if you see, as I mentioned, is mostly hydrogen in the composition wise. So which we can also recover for pure hydrogen production, which I have not used it. But it also in the same, we also can use this as our feedstock in our first and second reactor as well. Then it goes to so, and the major component of separation in methanol is the methanol and water distillation tower. So if you see the distillation tower for the first distillation tower, which is named methanol water tower, where we have 12 stages, where the parameter, if you see the spec, where I have decided where the component recovery, which is methanol, at the over top is 0.995 and the reflux ratio is 2.5. So basically, using this convergence, we are able to get a composition of pure methanol almost 75%, where the water has been recovered mostly in the bottom, almost 0.96. But there's are traces of water. So then uh, this particular line of this particular line of crude methanol is then been fed into our second, which is a pure methanol tower, where the design wise has a more number of trays to increase the efficiency of separation. But in this time, the monitor spec is also almost the same, but reflux ratio is higher. So, and you can see the composition that we get in the top almost 0.98. But to consider, there is also traces of nitrogen and CO2, which will be in vapor form. So this it can easily end up to 99.95 of crude methanol, pure methanol. Then goes to a flash drum. When the flash drum, it flashes the CO2 and nitrogen, and it enables us to produce almost, as I mentioned, 0.98, 0.99.5 of methanol. So that's in the sense of our discussion in the process simulation. But I also have included a process simulation file together with the with the assignment as well. So in summary, we have successfully designed a 200 kg per hour of methanol plant using conventional syngas route, which is optimal formulation condition. And also we have through fixed bed and flashing and distillation well. So, and it also validates all the balances, which is in the state of mass balance and energy balance. Significant, we have also designed a framework for improvement, which is also I can add as an improvement where we can use as for a recycle or also hybrid feeds where the hydrogen can be recovered. So with that, I end my presentation.